Hello, my name is Cade Dodd.
I am Adrian Montero, and this is Team 11's final project presentation for ESET 462. Our project is a water level control system using a PI controller. This system represents the need to transport watercraft between varying heights of water. Our system sets the water to a user-specified value using a reserve tank to pump water into the tank containing the watercraft. The design process for the project was divided into these key steps. We needed to design the real-world system. This includes the pipes, the water tanks, and the custom mounts for the pump and motor. We also needed to mathematically define the control system so we could program the microcontroller. Then, we needed to tune the controller using MATLAB so the system could be stable. And finally, we needed to test the system to ensure everything was functioning properly.
This is a block diagram of what the system looks like as far as controls is concerned. For the input, we have a desired volume of water that we want inside of the tank, or the difference between the two tanks, which is then pushed into our PI controller. The reason we chose PI is because this is a velocity-based system, and so the derivative component does not factor much into changing anything about the system. Next, we add an additional input in, which is the anti-stall torque. Because of the mechanical friction in the system and the amount of force needed required to move the water in the pump in the first place, there is a minimum speed that the motor must be run at before it will actually affect the system at all. And so the anti-stall torque is there to make sure when we need to move at least a little bit, there's always some force required. This then is turned, the combined effort of the PI controller and the stall torque are turned into a PWM signal, which is sent to, or a function is used to convert motor velocity into a PWM signal, which is then will be pushed out as it will cause the pump to provide water volume over time to the system. Meanwhile, there's also a feedback loop provided where the scale measurement is used to determine how much water is currently inside of the primary tank, and that is used to correct the output of the PI controller.
Our water level control system was designed using Onshape, a browser-based 3D modeling software. Um, the components of the system are the target tank, a reservoir tank, a loss valve, and the gear pump. The gear pump was powered using a 12-volt DC motor, and the pump itself was resin printed to meet our tolerance specifications. The PVC pipes and the tanks were bought from Home Depot, as well as the bolts to put it together. A rubber sealant was used to make the system watertight. All the electronics were borrowed from the lab.
Modeling the system requires three components: the motor, the fluid pump, and the mass scale. The motor provides a driving force to the control system through the motor velocity. The motor velocity is found by multiplying the motor constant to the voltage PWM. The fluid pump is modeled by the volumetric flow rate it provides. This is found by multiplying the motor velocity to the gear constants and subtracting the loss of torque due to stall. The mass scale is modeled by multiplying the volume by the fluid density. Once all these components are gathered, the model is then converted into discrete time.
For tuning our transfer function, we created a characterization graph to find the motor velocity, which means we ran a particular signal through a constant signal through the motor, and then from there found certain data points such as the maximum value it reached, the k value, and the how much time it took to reach 0.632 or the tau value of the maximum speed, which resulted in a plant transfer function of the motor shown on the screen. G of s is equal to 0.089 over 0.07 times s plus 1. From there, we then found we tuned constants for a PI controller, p being 1.52 and I being 1019. From there, then finally, this was transferred into a discrete controller based on our frequency that we were running the system at. The P came out roughly similar but a little lower, and I came out a lot smaller because it is required to keep the system simple. So to analyze our controller, we ran a domain analysis of it running in the S domain using the previous P and I constants shown before. There are no zeros to it, and there's only one pole, which is at s equals 0, so the system should remain relatively stable. You can also see there was some step, we initially got additional characteristics from step info, such as the rise time, its overshoot, which is near 0 but not quite, and settling time of roughly around 0.3 seconds to reach its goal. Unfortunately, because this is a PI controller, the system does not technically remain perfectly stable. It gets very close to its actual value and then oscillates around it a little bit. However, this instability is mostly unnoticeable because, again, we are controlling velocity with this system, and it does not, because velocity will be changing constantly over time, or the required velocity, the minor offset oscillating around it will not affect the actual system in practice.
In practice, the system works by using the gear pumps to force a difference in water level between the two containers by measuring the weight of the desired container. Our system has a leak valve, which tries to bring the system back into equilibrium from the level the pump forced the water to be. This means the control system of the pump needs to account for this constant loss. While testing the system, we learned that a few design changes were necessary. First, the system had problems with leakage. That is why the final model is covered in a rubber sealant. The gear pumps also needed a redesign. The original gears had difficulty engaging and would get stuck. The paddle design improved this as it worked better with lower tolerances. The control system, in addition, needed to be modified experimentally. The required volumetric flow rate and the stall torque had to be tuned to the correct values. Ultimately, after all of these modifications to the system, it functions properly and it can maintain the water difference. A video of this will be shown on the following slide.
This one is much better. Much better. Well, this side is closed, but now it's gonna be pretty steady with
Usually more open.
open it all the way.
Basically, part of the problem is if it's too low, it just messes up.
Well, I mean, it's pumping the entire time.
Alright, all the way open.
It actually can't keep up with that. It's going max speed and it's not reaching its target.
Right. Although it is behaving correctly, i.e.
Yeah.
It
It's
can't,
doing what
but
it can, but it
Right.
physically can't keep up with that.
To initial.
any other demonstrators we want?
we'll show it off in class too. So.
By the end of this project, our group had several key takeaways from this experience, such as in skills that we developed and problems that we had encountered. In terms of the skills that we developed, we learned how to program and tune a PI system from the ground up, and also learned how to properly program and refreshed our memory on how to set the inputs and outputs for the controller. However, in terms of the problems we encountered, we learned a lot from that, such as when working with fluids, you can often have issues such as from leaking, improper data collecting, and other issues related to just trying to keep the system contained. While also we learned that when using resin in making anything, it can be great, but it also has some drawbacks, such as when we were curing the gears, we found some of them had improperly cured to where they had some issues when it came to tolerancing, which led to pieces rubbing together and installing. And then also resin itself is just brittle and can break under certain amounts of stress. We found that some of the gears were not meshing correctly, so we had a lot of issues trying to get those to work and properly function. As well as the motor would often stall due to improper forces or torques within the gears themselves, which we have learned from and we'll take with us as we go forward. Thank you.